Well, good afternoon, ladies and gentlemen. I'm sorry to interrupt your great discussions, which is one of the real reasons we come to these conferences anyway, to have the nice discussions, see our friends, learn new things, share things with our friends. I'm Paul Nielsen. I'm one of the past presidents of AIAA, and I'm the Master of Ceremonies for today. So basically, I get to introduce the person who introduces the person who introduces our speaker. It's a big job, you know? For me, this is always a great start of the year. AIAA SciTech is just such a nice event to start the year off. And I like it because I get to hear new ideas. I like it because I get to see great people. And I like it because I get to make new friends at times. So many of you out there I think I know, but if you're not one of them, make sure you come up and see me afterwards so we can become friends too. So now I officially convene the 2016 Durand Lecture for Public Service. Now we're going to begin our program in just a few minutes, but first, on behalf of AIAA, I really want to extend a heartfelt thank you to Lockheed Martin and especially the Space Systems Corporation, because it's really Lockheed Martin SSC, I think that's the sponsor of this particular event, whose incredible generosity has allowed us to come together, to hear from a distinguished individual, to talk with our friends, and to learn some things new. So thanks to them, we're able to do this great networking, and that's a real nice thing for us. Now, I get to introduce AIAA's Vice President for Public Policy, Mary Snitch. Mary, would you come up? Oh, you're over there. Great.
Happy New Year, everyone. I want to say again exactly what Paul said, that it's wonderful to be at SciTech at the very beginning of the year to see old friends and make new friends. And as it turns out, this is my last year as VP for Public Policy, so this is the last Durand lecture that I will be introducing the person who introduces the person who is speaking, which I'm very honored to do. When the board next meets in the spring, this job is going to be turned over to the very capable John Rose of Boeing, who is going to succeed me. And John and I have been working very closely together for a number of years, and he is going to do a stellar job, I know. I want to remind everyone, you heard about it this morning at the plenary, you'll hear about it over and over again, but this afternoon at 5:30, Jim Albaugh, president of AIAA, is going to be speaking to the full membership about the governance changes that are underway, very important changes for the growth and sustainability of the Institute. And so I hope that you will go and listen to what Jim has to say, hear about all of the work that has gone into this governance reorganization, if you will, the new governance structure, and offer your support and, of course, offer your questions. And then when the time comes in the spring, vote, because it is critical through the terms of our Constitution that we have a very high voting percentage on the favorable side of the changes. So I hope that you will join me in doing that. The Durand Lectureship is the responsibility of the Public Policy Committee. We work every year to identify really distinguished science and technology leaders in our community who have distinguished themselves in such a way that it benefits mankind overall. The awardees since 1983, and we haven't had an awardee every single year in all of these years, but these awardees are people such as Norm Augustine, Sheila Widnall, Mike Wynn, and others. And so today, we are going to be honoring and recognizing Dr. Ron Sega. Ron, of course, is a friend, not only in the aerospace industry, but also in the broader STEM community, and has done so much in the world of science education. So I am very pleased to introduce my boss, Dr. Robbie Samantaroy, who is Vice President for Technology and Innovation at Lockheed Martin, who will come to the podium and introduce Dr. Sega. Robbie? Thank you.
Thank you, Mary. And luckily, I'm the last introducer. So this is not some infinite series. I think there's some Zeno's paradox or something here that we can, for you mathematicians in the room, can joke about. So very briefly, let me give you the honor of introducing Dr. Ron Sega. Dr. Sega is really one of those really impressive individuals that embodies a life of service within the government, both on the civilian as well as on the military side, as well as having a rich history and experience within academia. And even though he hasn't actually been in industry per se, he's done a lot of consulting with industry. So he's one of these individuals that really has been involved in what I call that three-legged stool that's so important for our national science and technology enterprise, which is industry, academia, and government. Some of the highlights of Dr. Sega that I think we should all be aware of. So currently he is the director of the Systems Engineering Program at Colorado State University, and that's going to be the basis for some of his comments today that are going to focus on the broad systems perspective across the aerospace industry. He has had a long, illustrious career in the United States Air Force, both from a uniform perspective, but also from a civilian perspective when he was the Undersecretary of the Air Force from 2005 to 2007. And he was also the Director for Defense Research and Engineering from 2001 to 2005, which is a very illustrious position within the Office of the Secretary of Defense. The other important thing that we should all know is that he was an astronaut from 1990 to 1996. And he actually logged a total of 420 hours in space on STS-60 as well as on STS-76. So given this lifetime of experience across all these various sectors, I'm really looking forward to the comments that Dr. Sega is going to give to us today on thoughts on complex systems and solutions in the 21st century. Join me in welcoming Dr. Ron Sega.
Well, thank you, Robbie, Mary, and Paul for those kind introductions. And it's really an honor to be here, and I'm humbled to be the presenter for the Durand Lecture for Public Service talk today. I made the title with a fairly low bar of Thoughts on Complex System Solutions in the 21st Century. Hopefully there will be a few good thoughts in there as well. Professor William Durand was an amazing individual, so I went back and did a little work. He obviously served a little bit in the Navy, naval propulsion, aeronautics, methods of research, engineering methods was clearly an area that he pioneered, as well as the public service of heading up in a CA for civilian as it got started, the initial days of looking at the National Academy's increased emphasis in engineering, then serving on the equivalent of the engineering division of the NAE, working with the National Research Council as kind of the working arm for doing studies and so forth, and then called at an older age, but he was obviously very vibrant as he went to 99 to help lead the development of jet engines for World War II. So quite an individual to have an award named after, and I'm honored by that. So let me see if I can find the advancer here. We're going to go quite quickly through a series of slides. And I want to look at this issue of systems in the development of complex systems and the progress of systems engineering, and as it is developed principally in the aerospace community to deal with these levels of complexity and what I think is a evolving need for the discipline developed in aerospace to be applied to other complex segments and problems in our society. So I'd start kind of a wake-up call for the United States of Sputnik in February of 1997. From a design standpoint, it was pretty good. The goal was to have an orbiting satellite and to be observed. So the antennas provided a signal that you could hear. The shiny ball provided a reflecting surface that you could see it. So as a little boy in Ohio, I do remember going out and looking for this dot that crossed the sky in northeastern Ohio. But it was a wake-up call for us. Then a bit later, in '61, of course, Gagarin makes an orbital flight. And in the design of that vehicle, they actually have an ejection seat. It came down in a parachute just to give confidence that you could, in fact, land safely from that flight. But for us, then, it was a matter of getting busy, having a clear goal, a clear objective, resources, and an energizing function for those that would be working behind Mercury, Gemini, and Apollo. For me, growing up in Ohio, I never thought I'd be one of those folks that would go to space, but it was one of those things that encouraged science and math education. I was at John Glenn's 50th anniversary celebration of Friendship 7 at Ohio State on February 20th, 2012, and he challenged the audience to name the number of computers that were on Friendship 7 during his flight, and the answer was 0. But we were in orbit that day in 1962, and we weren't able to go in orbit in 2012 on that day. So we go through a series of steps of going to the moon. And we test a lot. We build a lot of vehicles, and we learn a lot stepwise. We take some risks. Many of our designs were single string. In the case of Ed White's flight here, we were learning a lot about life support systems as well as the issue of orbital mechanics. At least from an operational standpoint, when you push the propulsion system toward the vehicle, just like a fighter, you end up going to a higher orbit and then sliding back. And so you have to have a little different strategy in space. Then by the time we get to Apollo, we are successful on a goal of the nation to go to the moon and return. I would say that we also have to be cautious about how we set goals. If it was a goal of exploration and the moon was kind of one major milestone in that route, we may have thought about the Apollo differently, but there was other contexts of political and so forth that surrounded it. So we had a team that worked hard, and some of the formalism of system engineering is generally traced to this era of post-World War II. So Apollo-Soyuz adds another element in what I think is a continuing trend, of course, in the 21st century, is that of culture. So working with others and to look at how you go about making sure that you have the strength of diversity ideas and so forth, and also the understanding of culture and backgrounds of folks that come there. We had a question about exactly how we do the welcoming in the Mir station, which was my second shuttle flight. Whether or not you'd shake hands in the hatch, in the doorway, which was not something you generally do in Russia, but in a hallway would be fine. So cultural piece there. Then on to discovery. A lot of requirements, clearly, in the shuttle program of what the shuttle would do. And some of the margins were not robust, but we pushed in advanced technology a great deal, whether it be in flight control, fly-by-wire, thermal protection systems, brakes, and so on. Huge success for the program. And the AIAA, we had a Horizons Forum, and Dr. Hans Mark was one of those that gave I thought was a brilliant history of that development of the shuttle program during those eras. Then for me, first flight was STS-60. First time we flew with a Russian cosmonaut, in this case, Sergei Krikalev. The symbol of, on the flag clearly, on the patch is the flag of both countries. And as the junior person, I was the patch designer. So one of the things in the patch was this thing called a wake shield. And so I had the opportunity prior to joining NASA to work on this wake shield at the University of Houston and with others. And the goal was to have this disk sweep out the drifting Maxwellian gas and create an ultra vacuum behind it. And it had a, so I was the co-principal investigator and program manager on this satellite. So it was a good thing to get your hands on hardware. And unfortunately, you know, we as a team made some mistakes. I had joined the astronaut program in the middle of its development and ended up being ready about the same time it was, so I flew with it. So the weight was not a constraint. We had a quarter of the payload bay at about 4,000 pounds. So for the purposes of creating a vacuum, we needed a material that didn't outgas much. And so stainless steel 304L was the surface of the wake shield that you see there, being lowered into a vacuum bell to protect it a bit from the environment and the processing of the cape, so that we had a shot of creating an ultra vacuum, and then that spider structure is to create a thin film in space. So the crew was a great crew, bringing folks together. The leadership there was Charlie Bolden. I think you know his current position at NASA, but he was a great leader and spent a lot of time to integrate our cosmonaut crew members and their families. There was a prime and a backup crew member with the crew and with our culture, increasingly important in big complex systems development. So we launched in February of 1994. Again, crew got along spectacularly. Part of the team, a larger team, on the ground, helping during the flight, much larger team getting ready for flight, and no, we're not stuck in the tunnel. So we did it all. So now it's time to deploy the wake shield. I was arm operator, so far so good. Put it out there, and we had tested the attitude control system. The sensors is looking at the CO2 line in the on the Earth's limb. Everything worked fine at the factory, at the right fidelity of the signals. Had integrated it. I was this time training for the flight, and I wasn't part of this. And the processing occurred for it onto the wake shield. Cables were laid down on the ribs and tied together. A continuity check was done. We went to orbit, and it didn't work. So why was that? Well, we hadn't tested in final configuration at the fidelity of the signal that we were going to be looking at. The power cable and the signal cable were locked up together. There's electromagnetic interference between the power cable and the signal cable. And so it was not to be that we were going to fly 40 miles from the wake shield to keep out of the, that environment. But we had plan B, which was a gravity gradient kind of orientation of the shuttle, so it didn't have to do any thruster firings. We could still keep the wake shield into a pretty pristine environment and meet our two objectives of characterizing the ultra vacuum that was created, as well as the thin film. Then there's a failure review board occurred. I participated in that, and in fact, this is kind of a nice picture of the Aurora Australis here. I put some of that Stimsonite tape on in the 195-foot level when the shuttle was vertical, and then on the second and third flight, it was successful. So systems engineering traditionally has been get a degree in a discipline, work for a long time, make a lot of mistakes, such as this one, get old, and they say, well, you're pretty old, you've made a lot of mistakes, you've learned from a lot of them, you're a systems engineer. So our goal is to kind of shorten that process a bit with education and so forth, and it's increasingly important that we have top quality systems engineering. Education and experience, I think, is important. So the next is the beginning of the 21st century, last kind of 15 years, if you will. Okay, so from, as was mentioned by Robbie, 2001 to 2005, Director of Defense Research and Engineering, we had three areas of particular emphasis. One we called National Aerospace Initiative, one in aerospace clearly, another one in surveillance and knowledge systems, another one in energy and power technologies. They're clearly related to one another. The other one I'd point out is the workforce issue. And that is particularly important for us going forward. So to do the complex systems, we're going to have hardware and software, capacity and test facilities and so forth, but people and talent is absolutely crucial. So we established a National Defense Education Program. It still lives today through a SMART scholarship and NDSEG, National Defense Engineering and Science graduate fellowships, as well as some work in the K-12 system. And by and large, the areas of emphasis are continuing to this date as well. Now, National Aerospace Initiative, we looked at, from left to right, high-speed hypersonics emphasis, space access, and space technology. So high-speed hypersonics, the easiest piece was to try to do things that would have an off-ramp in an expendable way. And so that eventually leads to the X-51A program. And then to reusable on that chart, and the reusable could then evolve to the air-breathing first stage of a second stage rocket. So space access, potentially coming off of airfields going forward in the 21st century. The other is looking at reusable launch vehicles that could be a vertical landing. Remember in White Sands, and this was a ways back when Pete Conrad was in the trailer there, DCX, doing a vertical takeoff and landing there at White Sands, a small vehicle. If you're going to go to space rapidly and have rapid access, for a variety of reasons, then the payloads also have to be responsive. So if you get there fast and it takes forever to check it out, that's not helpful. And so the idea of combining the system so that it would work together, so if you're going to be rapid, particularly on the small end, as we emphasized it earlier on, then you would be able to launch it quickly, build it quickly, and operate it quickly. And so for purposes of science and technology, more access seemed to make sense. For the ability to do risk reduction of the larger satellites to get to the relevant environment seemed to make sense. For reconstitution of satellites, as well as reducing revisit time, all seemed to make sense to emphasize some of the smaller satellite work. So the X-51A, we had 5 tail numbers in the program because it's a test program. Not everything is going to work. By the time I had left in 2007, they did get down to 4. And it turns out that 4 was needed. And the fully successful flight, climbing and accelerated and cruising at Mach 5.1 occurred in 2013. The team was really important. So it had NASA folks on it, it had folks from the DoD on it, worked together as a great team for a number of years and accomplished, I think, something that's very, very important. On the energy side, the idea is looking at it as a system. To enable more electric force was our goal. We had power generation, energy storage, power control, and distribution. Any one of them may provide a little bit of contribution, but together they enable system capacity, system capability that we were going to need. Whether it be in air, space, underwater, on land, it turns out that we're getting a great deal of help from the commercial side, especially on the land piece of hybrid electric technologies. Then as Undersecretary of the Air Force, had 3 kind of portfolio, space, research and development, and energy, and as number 2, you do what number 1 wants you to do, so that was the other part of my job. So in space, in addition to the executive agent for space roles, looked at acquisition there in a bit different way. We called it back to basics. And the idea of discipline, systems engineering was very important parts of that initiative. So system engineering, workforce, underpinning the idea of back to basics. Research, alignment with needs and redistribution of risk between the R&D community and the product centers was important. And as well as energy. We had about an $8 billion energy bill per year in the Air Force. We wanted to reduce it significantly, so we needed a strategy. So we had overruns for various reasons in cost and schedule. Some large programs such as SBIRT High and so forth. We were bound and determined to look at a program that we had early on, which in this case was GPS 3, call it 3A, because we wanted the ability to continue to evolve it as time went on. But at the same time, we wanted to make sure that what was really needed was identified. And what we knew how to do was in that subset. And things that we didn't quite have the technology in terms of its maturity, it would go on potentially 3B, 3C, and so forth. So in this chart, we see an evolution of a technology going from science and technology, TR levels 1 and 2, if you will, to technology development, 3 and 4, systems development, 5 and 6, and then to system production. And so you had an evolution of technologies. You know, they would kind of wean themselves off as you go up in terms of which ones were working. But you'd also have a development of people. You would have rhythm of production along the top. And so things could earn their way on in a sense of being baselined and still having risk in them. So the cross-links was relegated to looking at maturing and earning its way on the 3B, for example. So you baseline what you knew how to do, you let something that had higher performance earn its way on. Also, as I mentioned, the small satellites, whether it be in an ESPA ring, which is on this Atlas V flight of STP-1 in the spring of 2007, or on the smaller vehicles, was part of the idea. The energy strategy was making energy a consideration in all we do. So if that object, in this case a table, you could think about it as something else, needed to go to theater, you'd at least ask the question, did it need to go today? If so, it may have to go on an airplane that's pretty empty. But more often than not, it would be, oh, tomorrow is fine. You optimally load it and off it goes. So there was a operational consideration, there was a technical one, there was a financial one, there was a variety of people in the team that looked at how we would look at energy across the Air Force from a supply, demand, and culture standpoint. We ended up winning the Presidential Award for Leadership in Energy Management for the U.S. government as a team. So you looked at what makes sense with local and regional considerations. So one of the local consideration is if you have a vehicle for an Air Force base and the speed limit is 25 or 30 miles an hour, why buy something that goes 120? So low-speed vehicles was part of the plan. If you have a lot of wind in Wyoming, maybe put some wind turbines up at F.E. Warren. A lot of sun in Las Vegas, photovoltaics at Nellis Air Force Base working with the local community. That's kind of the common sense strategy. Then I had a position back in 2010 and 13 as Vice President and Enterprise Executive for Energy and Environment for both Colorado State University and The Ohio State University. And we had a conference in the 150th anniversary of Lincoln signing the Land Grant Act, where we looked at energy challenges for the next 50 years. So that was the goal. Explore what the energy challenges were, and then look at what role the universities could play. Pretty widely attended. The people from 31 states, 50 universities, 7 presidents were in attendance. We also kept the total number of people relatively small. Panels were made up of 2 from the university, 2 from industry, and 1 from either a non-government organization or government. So it's interesting in the challenges that came out of this. Number 1 was to create breakthroughs and approaches in integrating complex energy systems. That is an area that has been developed by this community. And so some of those skills and experiences have been developed over the last several decades are important, I think, for other sectors. Energy is clearly one of them. We looked at the efficiency of buildings and storage and renewables and biofuels and clean coal energy, nuclear, water, but all leading to also a national energy policy. So what can the universities do? Clearly, higher ed should be front and center for helping with the workforce. And also there was an opportunity to create test beds. For example, campuses, Ohio State has about 100,000 people on an active day on the campus. They have buildings that look like administrative buildings, laboratories, they have athletic facilities, some that look like industrial kinds of things. But you can use these kinds of things as test beds. Also, in some of these systems, there are a lot of people. Some communities will say demand-side management is great. Others will say no. Why is that? What is the dynamics of people working inside this large system that needs to include other disciplines beyond ours in engineering? For example, if we looked at an energy system and say, this is some of the folks at SEI and Paul Nilsson and so forth up in the cyberspace would be all over this, but the aerospace community energy, those disciplines seem to be very important for things that are right in the dead center. For example, what we normally call a smart grid. So if we looked at the second shuttle flight and think of it from energy standpoints, this was 1996 on STS-76, and we're going to the Mir space station. So the launch is separating from the grid, okay, in this energy context. Here we have the shuttle in space, kind of an energy island, using liquid hydrogen and oxygen, consumables for our power needs. The Mir space station on renewables and batteries. As we go to a docking, think of it as a plug-in hybrid, space version. So in a sense, the aerospace community has done this, albeit not at the scale that we need in terrestrial applications or at the cost, but there's a lot of lessons to be learned. Little City, International Space Station. Others are looking at doing this kind of thing. This happens to be Fort Collins, a deployment community. And so the idea of looking at complex systems and having it apply in other sectors of society seems to be the right thing to do. Last is the future trends and implications. So as we probably have Professor Durand to thank for much of this work that we have providing for government and other folks from the National Research Council, National Academy of Engineering. I had a chance in 2010 and 12 to participate in 2 of these studies from the National Academy. The one on the left is I chaired the Controlling Cost Growth of NASA's Earth and Space Science Missions, and then presented it to the NAC for NASA, to their leadership, and to folks in Congress. And the second vice chair of NASA's strategic directions, and as we said, and the need for national consensus. And so as you look at large complex systems, particularly where they involve government and the public sector, it's going to have a larger group of stakeholders, part of a larger system, if you will, not just the hardware and software pieces to it. And so as I testified before the full House on this for our group in December of 2012, the Science, Space and Technology Committee, it was only with the national consensus on the agency's future direction that we can really make progress. And so we did recognize that nearly all presidents had talked about Mars. It wasn't our goal to identify a direction, but it was important that there was a consensus for the country so that the branches of government would agree on this as a goal, set strategic goals and objectives. NASA could do a strategic plan, provide the ability and flexibility to manage that enterprise over a period of time. Global considerations. I think we, in this room, recognize there's many things are increasing. One is the rate of change of technology on a global scale. 2, increasing complexity in aerospace and terrestrial systems. 3, increasing the technical capacity of the global workforce. There's advantages, opportunities, as well as challenges. Increasing private sector R&D, clearly growing faster than public sector. There are systems and model-based approaches that can be applied to various sectors and disciplines. When you go to somewhere where we haven't been, you need to validate that the model is still good. You need to develop integrated test beds in some areas that we have kind of backed off a little bit on that. Also, the issue of cost optimization and affordability, increasingly important on projects, whether they be commercial, government projects. The issue of cost is important, and optimization of cost on a system-wide level. For this community, the idea, I gave a talk in AIAA in 2003 in Dayton on merging air and space. And so as vehicles are able to fly higher, some of them are in that Helios Pathfinder class, but others are in hypersonic ranges. So, and the test that we did in X-43A was at Mach 10 at 110,000 feet. You start to look at, you know, the idea of as we think of them as separate, the idea of thinking of them as a little bit more merged. If we have a two-stage, first stage air breathing, second stage rocket that kind of gets there, we eventually look at things that potentially are single stage to orbit. But in any case, the idea of thinking of them completely separate is probably something that we will see merging in the future. System approaches, I mentioned model-based system engineering and applying to other sectors. The evolving technologies of additive manufacturing and increasing autonomy, I think, are here and growing rapidly. The issue of spare parts, whether on the other side of the globe or out in space or at Mars or something like that, you know, how do you do that? Do you plan for some materials to be built en route to somewhere like Mars or on Mars? Do you take out some of the risk and actually get data in the development process of systems with the ability to tap into additive manufacturing? And obviously, increasing autonomy becomes important. Cyber is two-edged. Internet of Things allows many things to be cooperating in a more robust way. However, you're creating more points of entry, and you have to think about security. had the opportunity in 2015 to chair the study for the Army Science Board on the future of Army aviation. Mark Glauser, where are you? Stand up here. You're my vice chair here. Okay, there you go. And so this is one chart from this study that we did. Along the bottom, you see things that are opportunities in technology, cyber, manpads, UAS swarms, and lasers. There's also threats. And on the top of the slide, they are rapidly changing. The character of war is changing. Army aviation must change too. That's one of our main thoughts. So you need new concepts. Beyond the standalone platforms, and we talked about a joint battle space systems architecture and the CONOPS that would go along with that. The new systems we looked at are the UASs in various forms. Future vertical lift autonomy mission system is part of this architecture, this complex system that we want to view aviation in a slightly different way. So new prototyping, experimentation, test beds important, increasing innovation, and some risk-taking for disruptive kinds of things, leap ahead kinds of technologies. And so our tagline at the end is survive and win as an aviation system of systems. Finally, to the human dimension. The role of people, as I state here, the design, development, operations of human machine systems is changing. So as you look at more automation and more models and so forth, the question is, what is the role of people in sort of some of this design and development? But what about operations? As you look at a pilot, and the upper one was from the Air Force Research Lab, and then the bottom chart there is the front of the sea-based aviation with a kind of a UCAS right in the middle of the picture. And the question is, what does the pilot do? And so, you know, you have a lot of stick and rudder responsibilities back many years ago. Now it looks like more of a mission commander and manager of a complex system with UASs. World-class talent is essential. There's one takeaway for me, anyway, going forward in dealing with complex systems is talent. Discovery, innovation, workforce is clearly part of that. Also, leadership and management is part of developing these complex systems. So from a government and public sector, people that use systems thinking, that are looking at the rate of change of technology and looking at policy that makes sense, that's dynamic in a way of being able to keep up with the world that's rapidly changing. Teamed approaches. We're looking at multidisciplinary problems and multiple organizations. And it was alluded to a bit here, the partnerships of government, industries, and universities are important. I think there are new models out there of public-private partnerships that we don't have today that should be explored. At our university, Colorado State, I've been talking about system engineering in Washington, and the idea was the university said, we just started a system engineering program. And so you had to say yes. And so we have a Master of Engineering, Master of Science, and PhD. And it's to meet needs. So we started with aerospace, but applying it to energy, environment. And there's folks that are looking at healthcare and medical devices, financial systems, that are interested in adding some engineering kind of thinking to their economic sectors. And the program is offered, each class is in class synchronously and asynchronously out. So we're touching a working professional population offered in evenings. Finally, as I've laid this out, the evolution of systems in the 20th century, complexity clearly increased. The aerospace community led this more disciplined approach, the formalism of system engineering in the 50s and on, 60s and so forth. So as we look at the 21st century, this complexity didn't get any easier in aerospace and increasingly in terrestrial systems. And there's a global rise in technical and intellectual capability. There are great advantages of that greater intellectual capacity around the planet. There's also competition. Future trends, multidisciplinary martial organization, as I mentioned before, autonomy and cyber play key roles. And finally, the issue of the opportunities and challenges, I think, involve a team. Partnerships and policy between those entities, the government, university, and industry is important, but talent is what we have to focus on. Like Mary Snitch and ARCS and other organizations have worked toward providing additional scholarships and highlighting the importance of that to our future. So with that, I conclude this year's Durand Lectureship. Thank you for the opportunity to be here. Appreciate it.
see. Mary and Robbie, could you join me up here, please? Ron, thanks a lot for that. No more introductions. But I'm going to do the farewell to the person who's going to say farewell to the fareweller. No, I'm not going to do that. It's always a joy to be with Ron. Ron and I attended the same college, although we laugh about that being a college sometimes since it was the Air Force Academy. But he was a couple years behind me. But I remember even as a senior, people talked about this bright young guy coming up behind me. And he has proven to be a wonderful man and done so much for our country. Thank you so much. Now, on behalf of AIAA, I get to do the Olympic moment here.